Okay, folks, lesson 1.8, significant figures and measurements. Now we're getting down to it, aren't we, Mr. Hunter?
sig figs, I love them.
All right, so we're going to teach you, first of all, what the heck a significant figure is, and then we'll explain the necessity of having significant figures.
And you'll learn
That's
to
what we
hate
mean
them.
by sig figs. You'll learn to love them.
We'll learn. Anyway, determine the sig figs obtainable from measuring tools.
And be able to identify the number of significant figures in a given measurement. I would definitely recommend reading Chapter 2, Section 2.4, which would be pages 37 to 41 in your packet.
Okay.
Let's get down to it.
So measurements versus exact numbers. This is a very interesting concept. A lot of you are used to doing math where we use something known as an exact number. The exact number is a perfect number. If I say number 1 in math, it means it is 1.
No more, no less.
Exactly
1.
It's this type of number that is commonly used in your math class. It does not use units.
Okay, now let's contrast that with measurements. Measurements are never a perfect number. Measured values are gathered and used in chemistry from those measurement tools we talked about. There's a limit to how well you can know exactly how long something is or how massive something is, and that's determined by the tool that you're using. This limit causes uncertainty. Measurements are always uncertain, which is not true of exact numbers.
Yep.
And measurements always need to include a unit, which means we can't treat a measurement the exact way that we treat an exact number.
Yeah, so for example, real quick, just to give you a thought, if I say the number 10 with no unit, it is 10. If I say 10 milliliters, I know that there's approximately 10 milliliters there, plus or minus some amount, because the finer the measuring tool you have, the more you actually know. That might actually just not be 10. It might be 10.1582398 milliliters. And even then, that's not
That's
perfect.
still not a certain
it eventually runs out.
So that's where the issue comes up, is because we deal with measurements and we have to have a handle on what is the level of uncertainty in the measurement, and that's what the significant figures are all about. So let's go on to extend this concept a little further.
So significant figures, commonly referred to as sig figs or sig digs if you're with Mr. Ferguson, they are all the digits in the measurement that are certain plus one last estimated digit. And what do we mean by that? What do we mean by all certain digits plus an estimated? If you look at all these gradations here, every mark is a certain measurement. We know it's at least that much, and then we have to estimate what that last digit is, because unless it lands right on the line, then we estimate that last digit to be 0. If it doesn't end on the line, you have to estimate it to be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc.
And when he used the terminology "have to," and in order to correctly read the instrument, he's absolutely right. You have to estimate that final digit, and that final digit is your uncertain, because it's estimated. There's an uncertainty factor because it's an estimate, not a certain part of the measurement. And so the significant figures are basically everything that's a part of the measurement, and none of the placeholders that aren't part of the measurements we'll get into later.
So to determine that, we have to have major and minor scales. Everything has at least major scales. A lot of things have minor. A major scale is a numbered increment on the device. For this ruler, 0, 1, 2, 3, 4, 5. For this, 60, 70, 80, etc.
So the major scale on our ruler is 1 centimeter. The minor scale then would be those unnumbered increments that kind of split the area between the major scale. And we can see that these are tenths of centimeters on the ruler. And these are actually, if you take the time to count between 60 and 70, you see there's 10 markings. They are 1 milliliter minor scale on there.
Which means we have to estimate 1 beyond that marking. So we know the 1's place, we know the 10's place, we know the 10's place. Technology. We know, it's still there. We know the 10's place, we know the 1's place based on the gradation. We estimate to the 10th place on that ruler.
Okay, so let's actually put this into practice. We're going to go ahead and make a measurement on this ruler. So we can see the red tape starts at the 0, and it looks like it to me that it ends almost, but not quite, to the third mark
Yeah.
after the 9.
So I'm going with our major scale being 9, so I know it's at least 9.
That's certain.
And then I'm going to say it's 9.2.
Okay, the
For
2
certain?
is certain, because it's definitely more than 2.
Mm-hmm.
And then there's the uncertain part. It's between the second and the third one. Now comes the estimated digit.
And
We
this
have to
number
add
can
that.
vary between person to person. I'm going to say it's 9.25, let's say.
9.25,
But Mr. Ferguson might say it's 9.2.
6,
Yeah.
9.27,
Yeah.
9.24.
Yep.
Okay, so there's a plus or minus of at least 1 increment, and sometimes 2, in what would be a reasonable expectation there. So then we need to add the unit to make this measurement.
Because we measured it, we need a unit.
So
Yep.
9.25 centimeters. So that measurement has,
2 certain digits, 1 uncertain digit, which means it has a total of 3 significant figures.
all right, let's try the graduated cylinder.
All right, we already have a mark on it because someone changed it on me. But I can certainly say that it is 60.
Okay, so we're going to put
So
a
6 in the tens place. What do you think the ones is?
It is the 9th mark. It's 1
Okay.
below 70, so it's going to be 69.
And then we can estimate 1 beyond that because we have to. I'm going to say it's either 69.1 or 69.0.
Yeah, I think I can see most of that blue line, so I'm going to go with the 69.1. But I could see, it wouldn't be wrong to say 69.0 either.
Okay.
And then this is volume with the graduated cylinder, so that needs to be
Milliliters.
milliliters.
And you, the reader of the instrument, have to be able to determine what those gradations mean when they're on the minor scale.
So, just to hammer it home, nobody measuring this correctly would ever get the certain parts of the measurement different.
Yes.
That's always going to be 9.2 something centimeters. This is always going to be 69 point something milliliters. The uncertainty comes in only at the final place, which is our estimated digit.
Okay.
Both of those nut measurements have 3 significant figures.
Yep. So with all things in science, we have to have a rule. Well, because we like rules and they make things uniform, we have rules for significant figures.
This would be specifically when you're looking at a measurement that somebody else wrote.
Yeah. So you have rule number 1. Non-zero digits are significant. Well, that's an obvious one, but you have to say it. So if it's not written as a 0, you automatically know that number is a significant number. All zeros between non-zero digits are significant. So I'm going to write an example of that for you. What does that mean? Well, if I have 101 Dalmatians, I know for certain that 0 in between is a significant 0 because it is between 2 non-zero digits. And then number 3, all beginning zeros are never significant. And what I mean by that, 0.01, we have 2 zeros before the actual first number. They don't count for anything. They are place holding zeros. So don't ever count those as significant. There's only one significant digit, and it's right there. We have one significant figure in this one.
Okay, so the final 2 rules that deal with ending zeros, and this is really the only place that I think you can have some not sure. Ending zeros are sometimes significant, sometimes not. When are they significant? If there's a decimal point shown in the number, like if we wrote 10 decimal point. That 0, you deliberately do that. That you're telling someone the 0 is my estimated digit, and that. So if it's written without the decimal point shown, like let's say 1,000, none of those 3 zeros are significant. So you deliberately show the decimal point if you want those ending zeros to be significant. You don't show the decimal point if they're not significant. Okay? And the final rule is for scientific notation. The way and this actually, I love scientific notation for this reason as well. You always show all the significant digits in the measurement in the coefficient. The base or the exponent never counts. So if we're looking at 5.34 times 10 to the minus 12th
You only have
centimeters, There's three significant figures
If
in
you
the
have,
measurement.
if it's 5.340, that we know that 0 is going to be significant. It'll be
That
four,
would be four
sig fig.
significant figures.
That's why we always try to use scientific notation when possible and convenient, because it's not convenient to write 0.00000 times, whatever. All right, let's look at some examples, I think. When I said example, I meant post video questions.
All right.
But we will do two with you. Let's do one in each column, or just pick two at kind of random. Let's just pick two at the first. Let's do that one and that one for them.
Okay.
All right, so first off, we have 1,316 centimeters. How many significant figures is that? Well,
They're all non-zero digits.
they're all non-zeros, so
I'm
that
gonna say 4.
helps if you have it on pen.
That does. 4 significant figures.
Yep. All right, and then we have 0.00003.
Okay, so we have a whole lot of zeros there, but since they're all at the beginning, they're never going to be significant. So the only one that's significant is that's one significant figure.
All right, you're in charge of answering the rest of these 7. Do we want to do any type of scientific notation with them? Give an example.
All right, let's go 4.040 times 10 to the 15th microseconds.
Okay, give us how many sig figs are in that as well. And I think we want to give you a take 1-2 scientific notation as well, or not? No?
Sure.
Okay. So let's take 100, no decimal point.
100, no decimal point, millimeters.
Put that.
Put that into scientific notation with the correct number of significant figures.
All right. Good luck.